Biology is complex. This video describes the structure and function of the osteocyte, visualized on EM on the left, defined as the basic bone cell, resident in its lacuna, the space established when an osteoblast becomes embedded in the bone matrix it has created. Bone removed, two osteocytes on the right are star-shaped with multiple dendritic processes. This video will review important advances in bone biology concerning the osteocyte, reported in these two key references. As these concepts are based on experiments demonstrating osteogenic markers in small animals, this report provides photomicrographs that demonstrate these concepts in human specimens. 55 years ago, Dr. Lent Johnson, an expert on human musculoskeletal pathology, wrote a note of caution about the interpretation of data from small animals. Healing of fractures and acceptance of grafts in small animals are not an adequate basis for judgments of behavior in large animals and man. The cortex of guinea pigs, rats, and rabbits is less substantial than many cancellous trabeculi of man and may not give reliable data on the behavior of the human cortex. The COA Basic Science Course video series recapitulates original work by Lent Johnson and Don Sweet, including photomicrographs from the Armed Forces Institute of Pathology collection. We posthumously honor both consummate educators whose model for teaching orthopedic pathology has been replicated in part in the COA Basic Science course. This is a series of videos on bone biology totaling some 15 minutes, underwritten by Amgen, a biotechnology company. Consider reviewing them as they bring context to this series on osteogenesis, dynamically animating the skeleton at every level. The skeleton and the osteocyte are both complex and simple. The osteocyte is the controlling cell in the skeleton, and it is described as amazing in the complexity of what it does. The skeleton is an organ system that is so complex that it rivals the human brain. 46 billion osteocytes versus 86 billion in the brain, with similar spaces, and communication by a network of an astonishing trillions of connections. While the osteocyte and bone themselves are complex, there are simplifying concepts. Bone tissue consists of living cells enmeshed in one inorganic mineralized matrix, subserved by the osteocyte. Remodeling of bone involves a balance between two cell types, formation by the osteoblast and deletion by the osteoclast. There are three vectors that control the balance of remodeling: circulatory, metabolic, and mechanical, with the latter being predominant. The advances made in the references relate to osteogenic markers, the final common pathway acting within the three cell types, blast, clast, and cyte, to affect change. Finally, the radiograph demonstrates gross anatomy of the skeleton, demonstrating bone density, a spectrum reflecting normal bone in most, or on less bone as in osteopenia, or more bone as in osteoporosis. In the video series, pay particular attention to slides with a star, either red or golden. These cover key information that should be retained. The osteocyte, buried in bone in its lacuna, shows a large nucleus, scanty cytoplasm, filamentous cellular processes called dendrites, each entering a channel called a canaliculi. The array of canals, termed lacuno-canaliculi, a massive surface area of 1,200 square meters. On the right, with bone chemically removed, two stellate osteocytes extend multiple dendrites, part of this complex network, for communication with neighbors, surface cells, vessels, and even the marrow. The osteocyte represents 95% of the body's bone cells, each developing from a mesenchymal stem cell, or MSC, through osteoblast differentiation, living for decades and is responsible for multiple tasks. The osteocyte is a mechano-sensor that coordinates mechanical adaptive responses. Regulator of bone remodeling through control of osteoblasts and osteoclasts. Endocrine cell, sending hormones to other body systems and signaling markers locally. a regulator of calcium and phosphate and acid-base metabolism. This video may demonstrate in human material for the first time the staged formation of osteocytes. There is only one pathway to make bone. The osteoblast elaborates osteoid, predominantly collagen 1, to the surrounds. Complex biochemical steps in the osteoid over 2 to 3 weeks prepare it to accept the hydroxyapatite crystals. Mineralization occurs suddenly, 2/3 of the amount in a matter of hours, then slowly completing over the following year. Bone is not made in a vacuum, but rather requires a surface area for deposition, a three-dimensional template, which in man can be collagen 1, leading to membranous or woven bone, calcified cartilage, leading to enchondral bone, or pre-existing bone, either woven or enchondral, leading to lamellar bone. The template thus determines the initial bone tissue that has been created in the embryo. Woven, leading to the first cortex of all bones, and enchondral, leading to the initial cancellous trabecular array. All bone then remodels via lamellar bone formation. The osteocyte arises from MSCs, spindled in shape, in a series of transitions. Under the influence of osteogenic markers, OGMs, and in a favorable environment, pH, PO2, PCO2, other ions, and the extracellular matrix itself, stem cells move from a location around vessels, thus called pericytes, to become mature osteocytes, O, buried in bone in stages wherein the cell sequentially changes in structure and function. The mesenchymal stem cell becomes a pre-osteoblast, plumping up as it develops the intracellular machinery to make collagen 1, arriving at the osteoid seam where, elaborating osteoid, it becomes an osteoblast. Only 1 in 10 osteoblasts is selected to become an osteocyte. The other 9 disintegrate, undergoing apoptotic death. While burying itself in osteoid, the osteoblast transforms in sequential stages to an embedding osteoblast, EOB, osteoid osteocyte, OO, mineralizing osteocyte, MO, and mature osteocyte, O. This sequence occurs throughout life, regardless of the bone tissue that is being formed. To put the evolution of the osteocyte in context, we will first describe and then illustrate the initial steps of bone development. By definition, bone tissue is first recognized in the embryo at the primary center of ossification, or PCO, for each bone. The histologic steps demonstrating how this occurs are complex and are best reviewed in the videos Osteogenesis 2, circulation, and Osteogenesis 3, development of a long bone. In the simplest of terms, the external cortex forms through membranous bone formation as an applique around the bone model, be it cartilage for most of the skeleton or membranous for the skull, facial bones, and clavicle. The internal medullary space is termed the endosteum. In the center of the PCO, primary trabeculi are formed through enchondral bone formation. As soon as either type of primary bone forms, remodeling begins, in the cortex uniquely by lamellar bone, and in the cancellous array initially by woven bone and ultimately by lamellar bone. With rapid growth and clastic activity, the endosteum is partitioned into cancellous array on either end, and space between, which undergoes successive occupation first in the embryo and child by the bone-making blastema of fibrovascular stroma, then hematopoietic tissue, and ultimately in the adult, fat. The structure of cortical and trabecular bone varies throughout life. Videos Osteogenesis 3 and 5 will describe the details. The rest of this video will focus on the evolution of the osteocyte in bone up to the age of 1. Let's look at osteocyte formation when bone first forms in the femoral cortex of an embryo. Membranous bone formation, MBF, creates bone that is a porous scaffold as quickly as possible. Throughout life, MBF is activated whenever pathology produces a rapid loss of bone structure, as in fracture, stress reaction, infection, and rapidly growing tumor. All microscopic slides to be shown are hematoxylin and eosin, or H&E. About half this slide is early trabecular woven bone, stained red, and consists of many cells, which are osteocytes, and matrix, which is randomly oriented osteoid, primarily collagen 1. The other half is extraosseous space, filled with tissue that includes thin-walled vessels containing red blood cells. The walls of the vessels are thin and are not seen. Surrounding the vessels are cells of various sizes and shapes. The tissue is a form of blastema, in this case fibrovascular stroma, the cellular engine for making bone. Widely scattered red dots are red blood cells in vessels marked V. A fine capillary mesh, walls so thin that they are not easily identifiable. Such vessels are quite permeable and are termed sinusoidal. Bone marrow space is filled with vessels that have these characteristics. In this specimen, there is little new osteoid, as formation has just completed at 3 weeks. Fill-in remodeling is just beginning. This slide is the most important in this video. Mature osteocytes, marked MO, sense the requirement for structural reinforcement of the newly formed woven bone at 3 to 4 weeks post-formation. The open spaces filled with fibrovascular stroma are just beginning lamellar bone fill-in. Let us identify the cells that make up the stroma and show how the ultimate bone forms, clarifying exactly how the osteocyte evolves. Identify the slender MSCs, some marked SC, scattered throughout, sitting near vessels and thus are called pericytes. Under the influence of osteogenic markers to make bone, they become pre-osteoblasts, changing in structure. Carefully examine the slide to see examples marked POB. There are many POBs, however, that are not marked. No longer spindled, each is moving to the bone-forming surface, enlarging, developing the rough endoplasmic reticulum for protein production. At the bone margin, they become osteoblasts, OB, larger still, elaborating new osteoid, NO, scanty at this point at the edge of the bone. 9 of 10 osteoblasts disintegrate and die, the end products reused. One only is selected to become a resident mature osteocyte, MO. The following 6 slides will demonstrate in a human specimen the morphologic transition from MSC through pre-osteoblast, osteoblast, embedding osteoblast, osteoid osteocyte, mineralizing osteocyte, and finally the mature osteocyte. The chart outlines the various OGMs that are involved at each step. Note that this work, as outlined in the references, is in small animals and may not represent what occurs in humans. This slide in a different specimen shows detail. An MSC, the spindle cell, is circled. Purple-stained, mineralized, newly formed bone is on the left, crowded by a row of osteoblasts producing light pink, unmineralized osteoid in the middle. This is obliquely aligned on the pink-stained surface of new bone called the osteoid seam. Adjacent are pre-osteoblasts. These cells move to the osteoid seam, enlarging on the way. On arrival at the osteoid seam, the pre-osteoblast begins production and becomes the circled osteoblast, which has the appearance of a plasma cell, with an eccentric nucleus adjacent to the pale and stippled Golgi apparatus. The rest of the dark staining cytoplasm is filled with rough endoplasmic reticulum, the site of protein formation. 9 of 10 of these cells die in the process of elaborating the osteoid. How one osteoblast is selected to become an osteocyte is not known. Note the relationship with the mineralization front. Under an expanded array of OGMs, the circled embedding osteoblast continues osteoid production, eventually burying itself and at the same time degrading the immediately adjacent zone, making space that becomes the lacuna and the surrounding canalicular network. The cell also produces a dendritic array for contact with neighboring osteocytes and vessels. Fully embedded, the osteoid osteocyte has changed profoundly. The cell is smaller and has produced its lacuna and continues structural change, further refining the osteoid and completing the local communication network, dendrites, and canaliculi. At 2 weeks post-formation of the osteoid, the cell adds mineralization as a task and is now termed a mineralizing osteocyte. The process is complex, perhaps 70% occurring rapidly, completing over many months thereafter. An array of markers supports the biochemical steps, preparing the triple helix to accept the calcium hydroxyapatite crystal. With mineralization, the osteoid stains purple. Bone, it is said, has a conscience. If so, the mature osteocyte, here circled, is its entity, residing in its lacuna, notably smaller than the osteoblast. Its cytoplasm has lost its RER and Golgi apparatus. It is likely that the microarchitecture of pure woven bone, the dendrites and canaliculi, is more localized, communicating to neighbors and vessels, but lacking the long-range extensions of lamellar bone. Such osteocytes now populate this newly formed woven bone, which at 3 weeks is porous and weak. The model for you to understand this transition from pure woven bone to a reinforced mix of woven bone and lamellar bone is the human fetal femur at 3 or 4 weeks post-formation. On the left, the cortex is pure woven bone, mineralized but weak. There is adjacent skin, subcutaneous tissue, SCT, and primitive muscle, M. Focusing on the woven bone, WB, identify thick periosteum, P, primary trabeculi, blue cartilage core wrapped in woven bone, marked PT, and sinusoidal vessels, SV, in the marrow space. Reinforcement is undertaken by infill of the open spaces by lamellar bone formation, LBF, as previously described. In just 2 weeks, the cortex on the right shows less space and more bone. Now, several weeks later, the cortex is more robust, as you can see on the left. Virtually every element is more mature: muscle, periosteum, and the marrow space, which is one sinusoidal large vessel. The skeleton is a structure of constant adaptation. If we analyze the slide on the right, there are 2 patterns of bone. One, outlined in green, has many cells, enlarged lacunae, and less bone. This is the ghost of the woven bone that was present 3 weeks after formation. This became the framework whose open spaces are now filled with bone that is much stronger, lamellar bone. These circular areas, most marked with an inner purple border, are termed primary osteons. There are several on the slide. They are the key strengthening elements in this bone. Note that there are far fewer osteocytes present in the lamellar bone. No cement line is present, just emerging with the woven bone, which has many osteocytes present by comparison. The bone, then, is a mix of woven and lamellar bone and is termed fibrolamellar. The skeleton of the fetus and the developing child until 1 year of age consists of this type of bone. The osteocytes are no different in lamellar bone, but there are simply fewer of them. The following slides summarize the take-home message from this video. The first is on the characteristics of the osteocyte. The next is on the morphologic sequence as the MSC changes form and function on its way to becoming a mature osteocyte. The spectrum of bone types is listed. This video demonstrated the development of the osteocyte in woven bone and fibrolamellar bone at 1 year of age. The further development of the skeleton through the rest of childhood involves remodeling, driven by the formation of lamellar bone osteons, the basic structural unit of adult bone. These are formed by another complex collection of cells, a form of blastema, the bone multicellular unit, or BMU, also termed the bone remodeling unit. The mechanism is stress-driven and transforms fibrolamellar bone to adult osteonal or Haversian bone by the end of adolescence, to be discussed as indicated in subsequent videos. The final slide lists the osteogenic markers and the steps undertaken by the progenitor cell as it undergoes the transition to become the osteocyte. This remarkably complex cell, the ultimate multitasker that oversees all that happens with respect to the skeleton. Review the reference article for the complete story on the cell biological research on small animals, and recall Dr. Johnson's note of caution.